ones for doing one too.
Hi there. Today we're going to be looking at the paper called Learning Continuous Representation with Local Implicit Image Function from UC San Diego and NVIDIA. So this paper is dedicated to learning a system that can take a discrete signal, an image, in this case, and represent it in a continuous domain so that we can map it back from the continuous domain to an arbitrary resolution. So this is essentially a model that can solve the super resolution task. So we can take an image and we can see that the method performs much better than a simple baseline such as bilinear resize. So this approach allows changing the image's resolution in a continuous fashion, so we can produce animations like this where we can have a certain toggle and then we can just increase the resolution of the image and it becomes kind of blurry but still visually pleasing. So the approach that's proposed in this paper is part of a batch of papers that were coming out recently in computer vision dedicated to studying implicit neural representations. So there's an awesome GitHub repo that lists all of the papers that were coming out on these implicit neural representations, and essentially these neural representations are a way to parameterize different signals, including images, instead of having a discrete representation. Like for an image, we have a set of pixels in a 2D grid, and then for each pixel, we know the RGB colors for that image. So that's the signal that is known on a 2D grid. Instead of that, we would represent the image as a continuous function that can take a coordinate in the domain of the image, like a pixel coordinate, and then it can predict the color. So that way, if we have this continuous representation, we can change arbitrarily the resolution of the image, and for each pixel coordinate, we can compute this RGB color. So this is useful in a variety of different applications, mostly for 3D and 4D dimensional signals, where the memory requirements to store like voxel parameterized tensors is very high. So instead of storing all these voxel values, we can represent these high dimensional tensors as this continuous function that we can use then to map it back to the discrete representation. So if we can train sort of models that take, instead of a pixel-based representation of an image or a voxel-based representation of a tensor, they take this implicit representation, this function that is approximated by a neural network, then these models can fit much larger amounts of data into memory. So that's an interesting topic of research, and there's actually lots of papers that were coming out dedicated to this implicit representation. But sort of the few papers that we're going to be interested in today, and particularly this one, are dedicated to representing 2D images as these implicit neural networks. So the main approach of the paper can be summarized as follows. So on this figure, we see that the model in this paper takes an input image, then it has some sort of deep neural network encoder, and then this encoder produces a tensor of 2D feature maps for that input image, and then they have a sort of a function, a implicit function that is universal for all images, and they take these deep features and they take the pixel coordinates, and then this function can produce the signal, the image itself. So we can sort of parameterize this function by the deep features for the specific input image, and then we can change the resolution by changing up the pixel coordinates, and that way we can generate images with arbitrary resolutions. So they train this model in a self-supervised way in a super resolution task. So we have a training image, then we randomly downsample it and use it as an input to the encoder. And then we take the ground truth. So the ground truth is going to be used in our loss here, but also we take the pixel coordinates of the original image, and then we pass it to this implicit function, and it generates the image of the original resolution. So we take a pixel-wise loss like L1 loss that is used in this paper. So basically, they detach the image-specific feature encoder and the function that actually can map this feature representation back to the pixel representation of the original image, but it can this function can generate the RGB values for any given coordinate. So how do they do it? So the simplest way to do this is to parameterize this function f as a deep neural network. They have like a stack of fully connected layers, so like a multi-layered perceptron. And this function is going to take these vector z's. So the z's are essentially the feature vectors, the outputs of the deep encoder. And x's are a set of 2D coordinates in this continuous image domain. So if this function has the fixed argument z, then it's a function of x, and for any input coordinate it can predict this signal s, which is the RGB values for that image. So the feature vectors are called latent codes in this paper, and the simplest way to generate an image, so like presented here, is to take the closest latent code. So imagine we have an image and we have this 3x3 grid of pixels in the original image. So each pixel in the original image turns into a feature vector, a latent code z. And then we want to know the RGB values for a particular pixel coordinate xq. So we can take the closest feature vector, in this case z11, and then we put it into the implicit function f, and we also pass the coordinate of this pixel to the coordinate of this point to the function f, and then we get our signal. So that's the simplest way to construct an image like that they present. So that z star is the feature vector of the nearest latent code, and then they pass the coordinates of that point relative to this nearest latent code. So that is a simple way, but then they go on to add some tricks to this kind of encoding. So they first of all, they use concatenation of latent codes in a 3x3 neighborhood. So for each point in the feature vector tensor, they just stack these neighboring feature vectors into a single feature vector by also zero padding the borders. So that is also combined with this local ensembling approach, where instead of just taking the nearest latent code, which would result in a discontinuous output image because of sudden shifts from this nearest to this nearest latent code as the coordinate passes this point. So they take a weighted sum of the 4 neighboring latent codes, and they normalize the weights by these rectangle areas. So the weight for this latent code is going to be proportional to the area of this rectangle, and vice versa. The weight for this latent code is going to be proportional to the area of this rectangle. So they sort of blend the predictions from different neighboring latent codes and determining the weights in this kind of way through the rectangle areas. And that is the way they generate the image given this learned implicit image representation. And they also do something named cell decoding, where instead of having this function f of z and x, they also make this representation function dependent on the pixel value. So the simplest way is to decode the image is just to predict the signal in the center of the pixel. So x would be the coordinate that corresponds to the center of the pixel of the output image. So they also add these values c, which correspond to the height and width of the query pixel. So this function would also take into account sort of the output resolution. It would be aware of the output resolution, so it would also it would predict the color of not only the center point, but also given that we want to predict the color inside the pixel, and it has a certain neighborhood around that center point with a certain size. So they have pretty good results. So visually, you can compare with previous works. They have a more visually pleasing. The cool thing is that they can upsample the image to an arbitrary output resolution. So they train their model on the div2k dataset, which is a benchmark for super resolution. And then they test on the validation set of div2k and also a bunch of other benchmarks. And the div2k dataset has 2K resolution images and their low resolution counterparts with x2, x3, and x4 downsampling rates. So they also not only take these rates available in the dataset, but they also see how the model generalizes to like much higher downsampling scales, like up to x30. So here for this div2k dataset, they have the in-distribution scales and out-of-distribution scales. So they test their model on a extremely large compression rate. So they perform much better in all of these out-of-distribution cases, where they upsample the image to a much larger extent than in the training examples. And this also transfers to other benchmarks. This effect is present here, that they compare to previous state-of-the-art, and they also give the best results for this out-of-distribution high downsampling rate regime. So the implementation details are as follows. They do consider EDSR and RDN networks for the encoder. So these are just simple convolutional networks. So the EDSR baseline is actually very similar to the ResNet architecture. It has residual blocks very similar to ResNet, shown here in this 2017 paper. But the differences are they don't have ReLU activations in the end of the blocks, and they also don't have batch norms. But essentially, it's just a convolutional encoder, and then the implicit function is parameterized as a 5-layer fully connected network with ReLU activations. So they use 48 by 48 patches as the input for the encoder, and then the output ground truths are the patches of size 48R by 48R, where R is sampled from a uniform distribution. So they do an ablation study on cell decoding, meaning that they compare the implicit function that takes the pixel size explicitly as an argument to the baseline where it doesn't, and they show that it leads to images that are less blurry. And then also they show their performance on a super resolution task where they do not take patches from the image, but they use whole images of varying sizes from the Celeb AHQ dataset. So this is a face image super resolution task where they have ground truth images of various sizes, and since the implicit function allows them to not do any rescaling of the ground truth image, they perform better than just upscaling the ground truth images to the same size. So that's it. That's a simple approach that can represent an image in a continuous domain independent of resolution. I think this is a really interesting paper, and it can go beyond just super resolution as an interesting thing, just an alternative way to represent images. Instead of the pixel-based representations, we can take these implicit function representations of images and then use those to train different computer vision models. Thanks for listening, and till the next time.